Hey there, this is Math 8. We're looking at Unit 3, Lesson 1 on Understanding Proportional Relationships today. And this is our new unit that is all about linear relationships, and so today we're going to begin with the proportional part of those relationships there. We began today's lesson with a notice and wonder about two different graphs. We have a graph here where you have elapsed time there and a distance here. Over here we have a graph where there are no labelings for the x or y axes, but we do have a straight line that goes through there. And things that you might notice when you look at these two graphs, or you might have talked about some things like, well, these are all straight lines, aren't they? Right? So we have straight lines in each of these pictures here, each of these graphs. They're not curved, they're not bent, they're all straight, which is true there. We definitely have one that's labeled over here, and we have one that's not labeled over there. Something basic you might have noticed there. Another thing you might look at is that each of these graphs starts here at the origin, right? So remember that from before, maybe in 7th grade, that to be a proportional relationship, it does need to go through the origin, and both of these graphs do that, okay? When we look at this one here, for example, we also have two. We have F and G, and we're looking at the distance traveled. We could probably make some observations here as well. So for example, if I'm going to go in 3 seconds, for example, G has gone 6 centimeters, but F has gone 12 centimeters. So we could look at this graph and we can notice that, F seems to be going faster than G based upon how this graph is displayed there. Okay, you could probably make some other kind of notes as well. We could probably look and say that G, for example, as G is here, G seems to be going about if you look at G is going 2 centimeters every 1 second, isn't it? So it's going 2 centimeters per second. When we look at F in 1 second goes right there. There's F. F goes 4 centimeters in 1 second. So those are just things you might observe or notice looking at those two graphs, and we would probably say these are both proportional the way they're set up, but it's going to help us kind of go forward in the next activity. So in the next activity, it says moving through representations. It says that a ladybug and an ant move at constant speeds. So that's our constant. Remember back from 7th grade, we called that constant, we call it constant proportionality. We often label that with the variable k, but we'll get there later on. The diagrams with tick marks show their positions at different times, and each tick mark represents 1 centimeter. One thing you want to think about here, look at the start, is we're starting at where the heads of these little animals are going to be, right? These little bugs. That's our start at 0 right there. Okay, so as we look at our bugs, for example, we have 1, 2, 3, 4. I can make a line here. We're at 4 for this guy, and 5, 6 for this guy. Over here, we continue 1, 2, 3, 4, 5, 6, 7, 8. So this is at 8, and 9, 10, 11, 12, and 12 there. And over here, we're at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 for the ladybug, and then 13, 14, 15, 16, 17, 18 for the ant right there. I just want to jot those down so I don't have to count them later. I figure I'm probably going to need to know what's going on at some point. Okay? We have then down below, from this chart, we then have a graph. We have a graph that shows how fast or how much time it takes for the bugs to move, the ladybug or the ant. And so we have U, we have V, we have a y-axis with the amount's time, that's our seconds, and a distance over here or there. So this graph has been generated from the information up above, although we don't have labels on it to know which is which quite yet. So let's take a look at the questions that it's asking you today, and then we're going to have to refer back to this graph. The first question says that lines U and V also show the positions of the two bugs. So that's the graph part, right? U and V shows the position of the bugs. Which line shows the ladybug's movement and which line shows the ant's movement? Explain your reasoning. So let's take a look back here and decide which one of these is going to be the ladybug and which is going to be the ant. What might be best to do would be to take a look at a point, for example, here. For the ladybug, let's look at the ladybug. The ladybug seems to go 4 centimeters when it's at 2 seconds, whereas the ant is going 6 centimeters when it's at 2 seconds. Can we use that information to find that point on the graph? Probably we can. So let's take a look here. let's say that we went and we looked at this graph and we're going, well, what could that be? How could this work out? Well, what we might notice is that I do have some points along the line where I have a point here and it hits a point. Here I'm at different points on the grid where it lines up nicely. Over here I got points here, 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 and here. Okay, and so the graph though isn't labeled with numbers 1, 2, 3, 4. So it's hard for me to tell, well, where is a 4 centimeters and a 2 second going to be at, right? If I went 1, 2, 3, 4, right, and went, well, that's 4. If this is 4 seconds or 4 centimeters, if this happened to be my seconds, I could say that's 4 and 2, maybe. But again, I'm guessing on my labeling here. I'm just saying that's 4 and that's 2. If I went, this is 6 centimeters, which is what the ant is that happening at 2? Sure is. That does work so far for us. So just looking at what could work, time, if I continue this up here, 3, 4, let's take a look at 4. 4, it said, was right here. This ladybug goes 8 centimeters in 4 seconds. So let's see here. Here's 4 seconds, and here's a dot right there. Well, where's that going to be at? Well, that's 8. Sure enough, that does work. So what this is telling me here is that this graph U is going to stand for our ladybug. And so we can say our ladybug is line U, which would make our ant line V. And the reason I'm going to say that is because here at this point right there, I'm at 4, 2, and over here I'm at 6, 2, which matches what I have up here. Here's my 4 centimeters per 2 seconds, and here's my 6 centimeters per 2 seconds for the ant. So it seems to match what I have on this graph here, this little tick mark graph, and what matches over there. Okay, so that's just what I'm noticing when I'm looking at what's taking place there. So in terms of my reasoning, I'd have to think through, well, how would I want to explain that? And again, you probably want to explain that in your word form. So one thing I like to do as well, just as an added little thing that might help me later, is sometimes it's helpful to take a look at the information you have. And in this case, we have a distance, and we also have our time on this graph. Okay? And what we've seen so far for our ladybug and for our ant is we've seen this information. We can tell that so far, looking at what we have, is that our ladybug seems to go 4 centimeters in 2 seconds, right? So I can write down 4 and 2. And our ant, we said, was going 6 centimeters in 2 seconds, right? That's just given information from our initial chart there, and we use that to put our graph together right here. Okay? If we think back to what we've done before, sometimes we can find that constant or that k value by dividing our y and our x. In this case here, our x is our distance and our y is our time. All right, looking at our graph, that's our time, y, and our distance is the x value. And so when I take a look at this, I have a 2 over 4, or 1/2 is my k value. And here I have 2 over 6, or 1/3 being our k value. I like to make a table sometimes because it just helps me see things a little more clearly. This information here is really nothing different than the information here or the information here. It's just one more way of organizing it so I can take a look at it. But when I get to number 2, it sure does come in handy because it says, how long does it take a ladybug to travel 12 centimeters? Well, to go 12 centimeters, what I'm wanting to do is I'm going to take my constant proportionality, my k value, which in this case here is going to be 1/2 for the ladybug, and I'm going to multiply it by 12 centimeters. And when I do that, my half times my 12 is going to be 6. So in this case here, it's going to be 6 seconds. For the ant, we're going to do the 1/3 for our constant and multiply that by 12. And 12 times 1/3, or 12 divided by 3, is 4 seconds. So what are we asking here? What are they asking us to look at? How long does it take Ladybug to travel 12 centimeters? Well, let's take a look at our graph. 12 centimeters, it's going to be right here. So take a look at 12. We have 9, 10, 11, 12. So here's 12. And the question is, at what point does this cross my line, my graph? So there's one right there and one right here. So for the ant happens to be at 4. And for the ladybug, we're going to be up here at not 5, but 6. Now, is that what we said on our previous answer? The ant is 4, ladybug is 6. Let's see. Yep, this is our ladybug is 6, and our ant is 4. I probably should have labeled them a little bit better there. So I could use a constant proportionality to figure that out, or I could use the graph to figure that out and just see at what point do my lines cross or intersect the graph there. Next to number 3, it says to scale the vertical and horizontal axes by labeling each grid line with a number. You'll need to use the time and distance to show you the tick marks, which we've already done that. I guess I kind of skipped ahead. Sorry about that. So this is 2, 3, 4, 5, 6, 7, 8, 9, 10, and we went ahead and did that there. So ours is labeled, no problem, that looks good there. Check. Okay, so for 4, we're going to mark and label the point on the line U and the point on the line V that represent the time and position of each bug after traveling 1 centimeter. Alright, so the setup for that, what we're looking at really is what we might refer to perhaps as the unit rate. We're looking for where this is going to be at a distance of 1 centimeter. So that becomes our X value. So if you think back to what you did in 7th grade, we were able to set up an equation looking like this, so that y equals our constant proportionality times the x value. Well, the x in this case here, looking back at our chart that I made up above, was going to be 1. Okay, so that's our 1. But our constant for the ladybug was, we decided, a half. Well, 1 times a half is going to be equal to a half. So in terms of what about the ladybug, where is it when when x is equal to 1, when x is equal to 1, then y is going to be equal to a half. Alright, so our point is going to be 1 comma 1/2 for the ladybug, and that's going to be the position after it goes 1 centimeter. So I look up here, and if I go 1 centimeter, my ladybug is going to be right here at about a half, and that's my point right there at 1/2. When we take just a quick peek at the ant at 1 is going to be a little less, isn't it? It's going to be less than a half. Okay, so we look back over here, looking at what we had already. If for the ladybug we had 1 comma half, if I look at the ant's going to be at 1 comma something else. Well, notice this value, the half, even though we did a whole little problem there to get to the half was nothing different than my k value, my constant proportionality. So in this case here, the ant will be at 1 comma 1/3, and we could plot that on the graph and put that one right there as well. Okay, so could I label those? I certainly could, and I could have this being at 1 comma 1/2, and this one being at 1 comma 1/3 for where those points are going to be on that graph right there. Okay, and that's what we get looking at that one there. In terms of the Are You Ready for More, you can take a look at that to see how fast is each bug traveling. Okay, when you talk about how fast the bug is traveling, you're going to want to put that in terms of a centimeter per second, because we're talking about a time. So we're going to want our second to be our 1 value. So how many centimeters is it going per second is what we're talking about there. And so for the ladybug, when we take a look at the ladybug, how far is it going in 1 second? We'd say, well, here's our 1, and the ladybug is going 2 centimeters per second, and the ant is going 3 centimeters per second, based upon our graph right there. So we could say, and write that down in there, ladybug equals 2 centimeters a second, and the ant is going 3 centimeters a second. And just as a little review here, if you notice, what do you see is common between the ladybug's 2 centimeters a second and also the ladybug in terms of its constant proportionality, which is up here at a half. What we notice, hopefully we see there we have 2, and here we have 1 over 2, is that these two elements here are reciprocals, aren't they? So we can take 1 and we're basically flipping that over there. The same is true for the 3 and the 1/3. Okay, so will there ever be a time when the purple bug is twice as far away from the start as the red bug? Not really, because it's just, well, I'll let you explain that one there on your own, but nope, not really. Let's look at the next section, moving twice as fast. It says here to refer to the tick mark diagrams and graph in the earlier activity when needed. Imagine a bug that is moving twice as fast as a ladybug. On each tick mark diagram, mark the position of this bug. Okay, so it wants me to go back to my tick mark thing, and it's going twice as fast. Yep, twice as fast as a ladybug. Okay, so ladybug here is going to be at 4 in 2 seconds, right? We started at 0. So if it's going twice as fast, instead of being at 4, it's going to be at 5, 6, 7, 8. So maybe I put a little bug right here, give a little head, and there's my bug at 8. Okay. Over here, if it's at 8, doubling that, we're going to get to 16. So 9, 10, 11, 12, 13, 14, 15, 16. So put its head there, and there's number 16. And here we're at 12, so we're going to double that and get 24. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And there we are. Okay, so this little bug guy goes 8, 16, and 24. All right, what's the next question say? Got that there. Plot this bug's position on the coordinate axes with lines UV and then connect them with a line. Okay, so now we're going to take our plot here, our points, and make it part of the graph. So this little new bug was at 8, 2. He was at 16, 4, and was also at 24, 6. All right, so to plot that out then, I'm going to go to 8 and move up to 2 here. We're going to go 16, so we have counting by ones, right? 12, 13, 14, 15, 16. So 16 is going to be at 4, so we'll be right there. And in terms of the 24 and 6, that's going to be somewhere over here, isn't it? We're not quite sure that's going to be, but I don't have enough space on my chart right there. If I connect my lines, going through the origin and then hitting both of those points, I should have something that looks like that. In terms of my bug that goes twice as fast as the ladybug. Okay, so it's going twice as fast. It's changing how this graph looks compared to that one there, all right, and the order there. Our slope is a little bit different there. This one's steeper, this one's a little more flat, but it's going further as it goes along, okay, and a little bit faster. Write an equation for each of the 3 lines. Okay, so now we're back to writing an equation here for each of the 3 lines. This is where it might be handy to go back to our little bit of our chart before, our table before. We take our distance and our time. Okay, we go like this. And let's take a look at our ladybug, our ant, and our new bug, whatever that's going to be. We said before that when the ladybug went 1 centimeter, when the ladybug went 2 centimeters, it did that in 1 second. Okay. When it went 3 centimeters, it did that in 1 second. For our other bug, our double bug, it's double the ladybug, it can do 4 centimeters in 1 second right there. Okay. So for my K value, my constant proportionality, what I want to do is take here's my X, here's my Y, and we're going to do Y over X, which that becomes 1 over 2, 1 over 3, and 1 over 4. And for my equation, this is going to be Y equals K times X. So in this case for the ladybug, my Y is going to be equal to, well, we'll call it what it is. It's not really a Y, it's our time. So time is going to be equal to 1/2 times the distance. For the ant, time is equal to 1/3 times the distance. And for the new bug that's twice as fast as ladybug, time is equal to 1/4 times the distance. So that becomes that's how I set up my 3 different equations for those 3 lines. All right. So this lesson today had a lot that you're bringing back from 7th grade, so it might take a little bit to kind of recall those things there, but we're looking at making an equation from a table, from a graph, reviewing constant proportionality, and how that all works together. So in summary for today, it says that graphing is a way to help us make sense of relationships, but the graph of a line on a coordinate axis without scalar labels isn't very helpful. So very true. I mean, this is like a great looking picture, but because it doesn't have any labels, I don't know what it means. Okay, so it helps to label things and say what they're going to be. Without labels, we can't tell who's who. So for example, let's say we know that on longer bike rides, Kieran can ride 4 miles for every 16 minutes and May can ride 4 miles every 12 minutes. Here are the graphs. Well, that's great, but I don't know what is what. Okay, so without labels, I can't tell which line is Kieran's and which line is May's. Without labels and a scale on the axis, we can't use them to answer questions like which graph goes with which rider, who rides faster, if they started a bike trip at the same time, how far are they after 24 minutes, how long will they each take, right? I can't answer those kind of questions, right? But if I put labels on them, like here, now I can actually answer some of those questions. We can take a look and say, well, which one goes with each rider? Well, if Kieran rides 4 miles in 16 minutes, and I have it labeled distance, right, and minutes, and I go to 4 and I find 16, now I can notice, oh, that must be the graph that goes with Kieran, which means this is the one that goes with May, right there. Okay, so he's riding 1 mile, it takes 4 minutes. We have our rates here, 1 mile every 4 minutes. Those things are there, and with that I can start to answer some questions. So it helps to have labels, it helps to have numbers for you to be able to figure out information. In terms of who's riding faster, we could say, oh, May's riding faster because why? Going the same distance in a shorter amount of time, right? Here's our distance of 4, and in 4 we're doing that in 12 minutes, whereas Kieran's doing it in 16. Okay, so you have to be able to have that information, look at it. Do be careful though, because what you might notice is this, all right, common mistake kids make. On this graph we have time here and we have distance there. On our first one that we did a picture of, we had time, it's the same, time and distance here, and that's pretty normal. Sometimes though, these can get changed and reversed around, so be careful that you really do look at those labels and don't just assume that you know what it says there. Okay, let's take a look at tonight's homework. All right, Priya jogs at a constant speed, we're going to call that K. The relationship between her distance and time is shown on the graph. Diego bikes at a constant speed, twice as fast as Priya. Sketch a graph showing the relationship between Diego's distance and time. Okay, so this chart right here is going to be Priya's, okay, because it was already on the graph there, right? Diego, it says, is twice as fast. Okay, so to be twice as fast, I have to look and take a look at the first one and say, well, how fast is this one going? This one seems to be, if I find a point on the graph right here, here's a point, and look across, we're at 5. Priya is going 5 miles every, look down here, 1 hour. Okay, so to go twice as fast, and it's a proportional relationship, I'm going to multiply by 2 to end up with 10 miles in 1 hour. Okay, because 2 over 1, I'm not multiplying both parts. That's what I'm going to use for Diego. Now when I look at the value of this graph, I don't have a 10, do I? There's 6, 7, 8, 9, 10 is somewhere up here. I can't plot that very well. It's not going to work for me. But what I could plot is I could cut this in half. Let's divide both parts by 2. Okay? Divide by 2 over 2, which is the same as 1. 10 divided by 2 is 5, and 1 divided by 2 is a half, so we'll write that down as 0.5. And now looking at my graph, I can have 0.5 and I can move it up to here at 5, and now I have a point that I can use at 0.5, comma 5 there. And now I can draw my line here to here, and I can graph that one out, and that's what Diego's graph would look like there. Okay, showing it's going twice as fast. Number 2 says if you pick Blueberry Farm, a you pick Blueberry Farm offers 6 pounds for $16.50. 6 pounds for $16.50. Okay, great. Sketch a graph of the relationship between cost and pounds of blueberries. Okay, so to do this here, it helps if we take a look what we have. We have a cost, that's our y. We have blueberries, which is our x. And so I'm going to set up our pounds and our cost, our x and our y, and make a little table like this. What we know is that for 6 pounds, it's going to cost me $16.50. Right? That's what we know so far. So in terms of our rate, or our constant proportionality, our rate, in this case it'd be more like a unit rate, we could do $16.50 divided by 6. Okay? And $16.50 divided by 6 is actually equal to 2.75. So what does that number tell me? It says that if I was to get 1 pound of blueberries, it would cost me $2.75. Okay? So written as an equation, I could write this down as y equals 2.75 times x. Okay? So I could use this to fill in some more points on my graph and to see where I'm going to be. If, for example, I picked 0 pounds of blueberries, I put a 0 right there, 0 times 2.75 would be 0. Okay, so we have a couple points here. Here's 0, here's 1, here's 6, and we can plot those out. So if I pick 0, it costs me no money. If I pick 6 pounds, which is a little more than here, it's going to cost me $16.50, somewhere about here. Right, so here's my 6, comma, $16.50, something like that. If I did 1, it's going to cost me $2.75, so 1, comma, $2.75, and I have some points. Could I make some more points up? Sure I could. I could plug in multiple values here for this. I could plug in a 20 and see what I get. And if I did that, 20 times 2.75, multiply that out a little bit for you. And so when I do 20 times 2.75 times 20, we end up with 55. So if I put that on my table here, 20 becomes 55. I can make a 20 and I can go up to somewhere around 55, maybe about, I don't know, here or so, hard to say. And the point is I could plot it there and I can go through the origin and connect the dots and say that's what it would look like based upon how many pounds of blueberries I picked or how much it would cost me. Okay, so that's a nice way of looking at that one. Number 3, a line contains the points -4, 1 and 4, 6. Decide whether or not each of these points is also on the line, and this is a review from your last unit. Okay, so the way we do that, if you recall, is we're going to take our points that are given to find out what the slope might be first of all. So we're going to take our y values, here's x1 and y1 and x2 and y2, and I'm going to do a 6 minus 1 over 4 minus, and this is a -4. When I do that, 6 minus 1 is 5, and 4 minus a -4, it's like adding, becomes an addition problem. 4 plus 4 is 8. Okay, so 4 plus 4 is 8, and that's where I am right there. Now 5 divided by 8, written as a decimal, is 0.625. Okay, that becomes my k. It can also be considered my slope, and the thing that these all have to have in common is they have to have the same slope in order for that to be there. My y over k value needs to be the same for each of these that I have. Okay, so let's take a look at this one here. If I have and we'll use this point for our y value here, if I do 3.5 minus 1 over 0 minus a -4, that's going to give me, in this case here, 2.5 over minus and minus is plus 2.5 over 4. And 2.5 divided by 4 is equal to what? What's it equal to? 2.5 divided by 4 equals 0.625. Does that match our initial slope? Sure does, so that's going to work. For the next one, we're going to do 11 minus 1 over 12 minus a negative 4. 11 minus 1 is 10. 12 minus a minus 4 is 16. Okay, and you can do 10 divided by 16 to see what you get, and we end up with 0.625. Same slope, we're good. Next one, we do 50 minus 1 over 80 minus a minus 4. Okay, so we have 49 over 84. 49 over 84. And so 49 divided by 84 equals 0.583. That's not going to work, is it? Nope, not going to work. And for our last one here, we have a y value 2.875 minus 1 over, in this case here, negative 1 minus a minus 4. So what is that going to be? Well, that's going to be 1.875 divided by negative 1 plus 4 is going to be 3. So 1.875 divided by 3 happens to be 0.625. That would also be a solution. Okay, so our key here was to use the given values, okay, in order to find out our slope, and then choose one of those values to use and do a y1 minus y2 kind of thing to figure that out, or y2 minus y1, x2 minus x1, to solve and decide, does it have the same slope? If it doesn't have the same slope, it's not going to work for us. Number 4, it says the points 2, negative 4, x, y, and a and b all lie on the line. Find an equation relating x and y. Okay, so we're looking over here at this next one. So these guys are on the line, and we want to write an equation for this crazy old line. Okay, so to do that here, let's look at some points that we are given. Okay, so some points that we have. We have a point here, and we can see that A is located at 6, negative 1. Okay, we have a point here, 2, negative 4. We have a point over here of 10, 2. So we're given some points here to start with, okay, between A and B, whatever you want to look at. Because it's on the same line, it's going to have the same slope. So let's go ahead and use these two values to figure out what that slope is going to be. All right, that slope is going to be the y value here, 2, minus the y value there, negative 1, over the x value, 10, minus the x value there, which happens to be 6. So 2 minus 1 becomes 3, and 10 minus 6 becomes 4. So at this point, I have 3/4 is my slope for this entire line. So to find out or write an equation for the line relating x and y, which is this point here, x and y, I can now use this to, just like I did before, to figure out, well, what can x and y be? Well, let's take a look at these numbers here. It's going to be like this. Y minus a negative 4, y minus negative 4 over x minus 2 is going to be equal to this same slope, 3 over 4. Am I done yet? Not quite, because minus and minus becomes plus 4. So I can rewrite this as y plus 4 over x minus 2 equals 3 over 4. And that equation is just fine to show how y and x work with that whole line there. Okay, hope it helps you out. Long lesson today. See you next time.